Imagine two things you're tracking together. A learner attended the extra classes, and that same learner passed the test. Two yes or no outcomes, side by side. Almost every honest question you can ask about them falls into one of three buckets. Ask for the chance that both happened together, attended and passed. That's the joint distribution, the full picture of the pair. Ask only about passing and let attendance fall away entirely. That's a marginal distribution, one variable on its own. Or ask about passing given that they attended. You've been handed a fact and you fold it in. That's a conditional distribution. Three questions, three tools. Let's build all three. Here's the cleanest way to hold two discrete variables in your head at once. A table. Let x take the values 1, 2, 3 down the rows, and y take 1, 2, 3 across the columns. Every square holds one number. Little p of x, y, the probability that x equals that row's value and y equals that column's value, both at the same time. That single square is the joint distribution, one cell at a time. A valid joint table obeys just two rules. Every entry is at least zero, probabilities are never negative, and every entry added up across the whole grid comes to exactly 1. All the probability lives inside this table. Nothing leaks out. Let's put real numbers in and actually compute. Here's a concrete joint table for x and y. Take a moment. You can already see every entry is non-negative, and they all sum to 1. Now the marginal of x. To get the chance x equals 1, ignoring y completely, we sweep across that row and add every cell. Sum over all of y. That's what summing out means. Row 1 gives 0.1 plus 0.05 plus 0.05, which is 0.2. Row 2 adds to 0.35 and row 3 to 0.45. Those three numbers are the marginal distribution of x. The marginal of y works the same way, only now we add down the columns, summing x out instead. Column 1 totals 0.25, column 2 0.4, column 3 0.4. These sums are written in the margins of the table, which is exactly why we call them marginals. And notice, the row totals sum to 1 and so do the column totals. The bookkeeping always balances. Conditioning is where the real intuition lies. The formula looks innocent. The probability y equals y given x equals x is the joint over the marginal of the condition. But here's the picture behind it. Say you're told x equals 2. That fact throws away every row except the second one. The whole world shrinks to that single slice, but those three cells only add up to 0.35, the marginal of x at 2, not to 1. A distribution has to sum to 1. So we rescale. Divide every entry in the slice by that row total. 0.05 over 0.35 is 1/7, about 0.14. 0.15 over 0.35 is 3/7, about 0.43. And the last cell is 3/7 again. 3 clean conditional probabilities. And the payoff. Add those three up. 1/7 plus 3/7 plus 3/7 is 7/7. Exactly 1. Conditioning takes a single row and stretches it back into an honest distribution of its own. Now, a special and beautiful case. Sometimes knowing x tells you absolutely nothing new about y. When that holds, we call them independent, and it has a crisp test. The joint must equal the product of the marginals in every single cell. Test our earlier table. Take the top left cell. The joint there is 0.1, but its marginals are 0.2 for x and 0.25 for y, and their product is only 0.05. 0.1 is not 0.05. One cell disagrees, and that is enough. These two variables are not independent. You never need to check the rest. A single mismatch settles it. So what does independence actually look like? Here's a table built to pass. The marginals of x are 0.4 and 0.6. The marginals of y are 1 half and 1 half. Check any cell. The top left is 0.2 and 0.4 times 1 half is also 0.2. Run the other three and every one matches its product. So here, x and y truly are independent. And there's a lovely equivalent way to say it. When they're independent, every conditional collapses back to the plain marginal. Knowing x really does change nothing. Let's run one all the way through, start to finish, on a small table you can hold in your head. Two yes or no variables. X is 0 for did not attend, 1 for attended. Y is 0 for failed, 1 for passed. The joint table reads, didn't attend and failed, 0.1. Didn't attend but passed, 0.2. Attended but failed, 0.3. Attended and passed, 0.4. First, always check validity. 0.1 plus 0.2 plus 0.3 plus 0.4 is 1, and none are negative. Good. It's a legitimate joint distribution. Now the marginals. Summing each row gives the distribution of x. The chance of not attending is 0.1 plus 0.2, 0.3. Attending is 0.7. Summing each column gives y. Failing is 0.4. Passing 0.6. What's the chance of passing given that the learner attended? Take the attendant pass cell, 0.4, and divide by the marginal chance of attending, 0.7. That's 4 over 7, about 0.57. Compare it to the raw pass rate of 0.6. Attending nudged the odds. The conditional and the marginal disagree, which is our very first hint that these two are not independent. Let's confirm it properly. The independence test on the same corner. The joint at 0, 0 is 0.1. But the product of its marginals, 0.3 times 0.4, is 0.12. 0.1 against 0.12. They differ, so independence fails exactly as the conditional warned us. X and Y are dependent. Attendance and passing move together. Your turn. Back to our 3 by 3 table. Here's the challenge. Find the conditional distribution of x given that y equals 3, the third column. Pause the video, work it out, and I'll wait, right here. Here's the walkthrough. First, the conditions marginal. Column 3 sums to 0.05 plus 0.15 plus 0.2, which is 0.4. Then divide each entry in that column by 0.4. 0.05 over 0.4 is 1/8, 0.125. 0.15 over 0.4 is 3/8, 0.375. And 0.2 over 0.4 is 1 half, 0.5. Add them, 1/8 plus 3/8 plus 1 half is 1. If you got 0.125, 0.375, and 0.5, you've genuinely mastered conditioning. Well done. One more idea that sits right on top of conditionals. Once you have a conditional distribution, you can take its mean. The conditional expectation of y given x equals x. Just the usual weighted average. But using the conditional probabilities. For each value of x, you get a number. So as x varies, this becomes a function of the random variable x, written e of y given x, with no specific value plugged in. It's itself a random quantity. And here is the jewel, the law of total expectation. If you now average that conditional mean over x, you recover the plane. Unconditional mean of y. So whenever you meet the expectation of a conditional expectation, you can collapse it straight down to the expectation of y. No computation needed. It's a shortcut worth remembering. Trap 1. And versus or. The joint, P of x and y, is both events happening together, an intersection. It is not the union, the chance that either one occurs. Comma means and. Trap 2. The wrong denominator. When you condition on x, you divide by the marginal of x, the thing you were told. Divide by the wrong margin and the numbers are meaningless. Trap 3. Declaring independence too early. One cell agreeing with the product proves nothing. Independence demands every cell match, but a single mismatch is enough to reject it. Trap 4. Skipping the sanity check. Before you touch a marginal or a conditional, confirm the whole joint adds to 1. And remember, a conditional is undefined wherever its marginal is 0. Let's tie the whole picture together. The joint, P of x and y, is the complete story of the pair. Every outcome laid out in a grid. A marginal is what you get by summing that grid over the variable you don't care about. One variable standing alone in the margin. A conditional is the joint divided by the marginal of whatever you were told. One slice, renormalized. So it sums to 1. And independence is the clean case, where the joint is just the product of the marginals. So every conditional falls back to its marginal. Joint, marginal, conditional, independence. Hold those 4, and two random variables will never tangle you up again.